Hello everyone. In this lecture, I aim to explain fundamentals of counting. You must have heard counting, permutations and combinations a lot when you start your any study related to probability, right? It is also taught in high school mathematics, and it is actually a very important concept. Even if you take subjects like statistics or probability theory in your college. So this is one video which should be enough for you to understand all the basically the different type of counting problems that you can encounter, what they mean, and what do they actually like how do you actually solve that problem. So for that, I'm going to cover a very simple example which is relatable to you, so that it becomes easy to understand, easy to follow, and it sticks. So in front of you is an ice cream parlor, and suppose you are in an ice cream parlor and you have decided that you want a double scoop ice cream, and there are 4 yummy flavors which you can choose from. So as you can see in the screen, this is an ice cream parlor and you have vanilla, chocolate, strawberry and mint choco chip flavored ice creams which you can choose from, and you have decided to take 2 scoops, that is a double scoop ice cream. And I would like to go through a very important theorem of counting, which actually uh, which actually explains any calculation you do. It is not sufficient. It's not that you should just know this theorem and everything will magically make sense. Counting is not that straightforward, but it is the fundamental for everything. That's why I'll just define what the fundamental theorem of counting is. I have also explained this in my previous lecture, so if you want a better understanding or more in-depth understanding of this, you can check that out as well. So, suppose that a job consists of k different tasks, and the ith task or out of those k tasks, each of the tasks can be done in ni ways. So, task 1 can be done in n1 ways, task 2 can be done in n2 ways, and similarly task k can be done in nk ways. Then the entire job can be done in n1, can be done in n1 into n2 into nk ways. Okay, so this is the theorem, this is what it means. So suppose if I have 2 tasks and the first task can be done in 10 ways. Suppose there are 2 subjects you have to choose from, okay, and not 2 subjects, there are 2 courses you have to choose from, and in course 1 there are 10 subjects you can choose from, and in course 2 there are 8 subjects you can choose from. So what are the different ways in which what are the different combination of subjects that you can choose? So again, by the fundamental of theorem of counting, you can say that that number is 10 into 8, which is 80 ways. Okay, and this theorem is can be very easily proved using the principle of mathematical induction. I have covered this in my previous lecture, so you can go through it. But this proof is not at all required for this lecture, so let's just carry on and try to understand more nuances associated with counting and the problems that come with it. So there are 2 nuances in this principle of counting. Again, now I say that a task can be done in one way, in n1 way, and another task can be done in n2 ways. Okay, and you just multiply it n1 into n2, and that is the number of ways I can do the whole task together. But there are 2 things that you should keep in mind when you are counting anything. First, are you counting with or without replacement? And second, whether or not ordering of tasks is an important thing. When you're counting, does it matter if you're ordering or does it not matter? So maybe you won't understand this completely when I'm saying it right now. That's why I have considered all the 4 possibilities, right? All the 4 possibilities that that are there, that with replacement ordered, with replacement unordered, without replacement ordered, and without replacement unordered. And if you understand this particular aspect, that what these four combinations actually mean and how you solve these problems, then I assure you 80% of counting and any permutation and combination problems can be solved very easily if you get a hang of this particular concept. So let's go to the ice cream parlor again. Okay, case 1 is ordered and without replacement, and here you can just consider this as two simple English words. What does ordered mean and what does without replacement mean? You can think of it as, I cannot choose 2 scoops of the same flavor and order matters. So I cannot choose 2 scoops of the same flavor means without replacement. Okay, this is what it means. And ordered means that, so order matters. To understand that, you can look at this graphic. So what this says is, if I say I want my first scoop as vanilla and the second scoop as chocolate, and if I say I want first scoop as chocolate and second as vanilla, they are not the same. They are two different cases when you're counting. Alright, and second, if I say I want 2 scoops of strawberry itself, then that is not allowed. So just assume you're in some weird ice cream parlor which does not allow 2 scoops of the same flavor. Alright, now what is the question? The question is, how many different ice cream combinations can you make? So you have 4 flavors and you have to choose 2. Alright, with these conditions, that you cannot choose the 2 same flavors, and second, choosing what you choose first and what you choose second matters. So this and this are actually 2 different, this should be counted as 2. It's not that, oh, I've taken a vanilla, I've taken a chocolate. So that's just that's the same thing, right? I'll count that as 1. No, in my case, in this particular ice cream parlor, these 2 are different ice creams. Alright, so let's try to solve this by the fundamental theorem of counting. Now let us consider this whole task as 2 different tasks. The first task is what is my scoop 1 option and options, and second task is what are my scoop 2 options. Alright, now since I have 4 flavors, I know that scoop 1 I have 4 options. I can choose any of the 4. And for scoop 2, now since I am not allowed to choose the same scoop, suppose I chose a strawberry in the first scoop, then I cannot choose a strawberry in the second scoop. So I only have 3 options left. So the scoop 2 options are 3. And now simply by the fundamental theorem of counting, I can say that my total number of options are 4 into 3, which is 12 possibilities. So there are 12 ice cream choices that are there if these are the conditions, and I actually have a small graphic for you as well, which explains what are the 12 ice creams that I can get. Now if you see the first one and the fourth one, they are actually the same scoops. Like if you look at if you focus on the scoops there, it is chocolate and vanilla. But since I am saying that order of my ice cream matters, I have considered this as 2 different outcomes of my experiment. It is not the same outcome. Alright, and hence my total possibilities are 12. And this particular situation, ordered without replacement, is a very common question and a very common problem that you solve, and hence we have a very common notation for it, which we call as NPR. It is this P means permutation. So basically it means that there are n so for our case, n will be 4 and r will be 2. So from the 4 choices that we have of ice cream, we are choosing 2, but the order matters. So in that case it is 4p2, which is, so in our case it is 4 into 3, right? And if and the definition of 4p2 is n factorial by n minus r factorial, which would be 4 factorial by 2 factorial, which is actually what we were getting. all right. So this is a very common notation because this was just like this we just had to multiply two things, right? If we had like 100 if we had to choose from 100 options 50, then it's easier to write this instead of doing this whole multiplication and writing it down, right? You can just write this as 100 factorial by 50 factorial. For those who don't know what this factorial means, it basically just means you go on one less and keep multiplying. So 4 factorial is this, 2 factorial will be 2 into 1, 10 factorial will be 10 into 9 into 8 into 1 till like that it will keep going. All right, this is also a common notation used a lot in permutations and combination, and the reason for that is we have a lot of multiplications going on here. You cannot keep writing down every possible multiplication that you have to solve. It's easier to write it this way, right? Now this particular thing 100p50, writing down 100 till 50, 100 into 99 into 98 into 97 doesn't make sense. So this is a better notation. And ordered without replacement case, we call it NPR. We solve it by NPR. So you have like, suppose you have 4 options and you have to choose 2. The order matters, and you cannot have the same thing twice. So then this is the way to go. All right, you can also solve it using this if you logically think of it, and a more elegant way of writing it is in the permutation notation. All right, also one thing I want to mention here is that there is also a 0 factorial just for purposes of ease. This is also defined, and this is equal to 1. There is no certain logic to it, it's just defined that way. All right, now this is the first case. Now let's go to the second case. Now I am saying ordering is still important and with replacement. So that means that I can choose the same flavor of ice cream twice. Now this ice cream person is a little more now the ice cream parlor is a little more it has become lenient, and it's saying that you can choose the same ice cream, but the order still matters. So now again, my scoop 1 option is still 4 and my scoop 2 option is also now 4. Reason is I can repeat flavors now. It's not that if I've taken a strawberry in the first scoop, I cannot take a strawberry in the second scoop. So in both the scoops I have 4 options, and again by the fundamental theorem of counting, my possibilities have increased to 16, from 12 to 16. And the reason is, if you look at the diagonals, these 4 ice cream scoops have been added as compared to our previous example. These were there in the previous case also, okay? Just this is added because now we have a with replacement case. This is actually the easiest case. If I had like 10 scoops also, it would just be 4 into 4 into 4 till 10, which is like 4 raised to power 10. So this is a common notation I have written here. So for our case it's 4 square. All right, if I had to choose 10 scoops, then it would be 4 to the power 10. If I had 10 flavors and I had to choose 4 scoops, then it would be 10 to the power 4. All right, great. Let's go to case number 3. Now in this case, unordered without replacement. Now again I cannot choose same scoop in both the scoops, but now the order doesn't matter. Okay, so if I go back to my previous case, right, I had written that this is not equal to this. It meant that this and this are actually 2 different options that you're choosing. But what now I'm asking is that no, these are the same. It just matters that what 2 flavors you're choosing, okay? Where what is first, what is second doesn't matter. And now I'm saying, now tell me what are the possible options that I have. If I count the total number of cases, what will that be? So again, now my scoop 1 option is 4, my scoop 2 option is 3, okay? But this, if I just do a normal 4 into 3, this is taking order into account, all right? this is not, so this basically is just giving me 12, which is our first case. And here 1 and 4, if you see, they are considered as two separate choices of ice cream scoops. But for my case, what I'm saying is 1 and 4 is actually just one option. All right, I just, for that ice cream person, he's just saying, you tell me what 2 scoops you want. I don't care what order you want it in. Okay, so now if you look at this, here if I have vanilla and mint choco chip, that is same as mint choco chip and vanilla. This ice cream person is very, he doesn't care what you take first. Okay, so if you take our example exactly, if you look at the 12 case that we have, each pair is being counted twice, right? This is considered once, this is considered two. All right, but for me this is just one case in this particular example. In this particular case, it is just one case. I don't want it to be two separate options. So what we had earlier, we just have to divide the result by 2, because each pair is being counted twice. You can see here, right? Any two possibilities you take, it is being counted twice in my example above. All right, so now in our case, now it is 12 by 2, which is 6 possibilities. So if you look at this vanilla and chocolate is one case. You don't have vanilla first, chocolate second, chocolate first, vanilla second, all that being considered as two different options. This is the same thing, and hence now we have 6 possibilities, and they are very neatly captured here, you can see. All right, so now my question is, we have 2 scoops here, right? Now instead of 2, what if we had 3 scoops to choose from? In that case, what would we divide by? And the answer is the factorial of 3, which is 6. So what this basically means is that if I am shifting from ordered to unordered, all right, if I'm shifting from ordered to unordered, every case, okay, like suppose here I had vanilla and mint choco chip. Now vanilla and mint choco chip, there are 2 possibilities in which it can be ordered. It can either be vanilla mint choco chip, it can either be mint choco chip and vanilla. All right, so I have to divide by by 2. The reason is that I don't want this to be as 2 separate options. So instead of 2, if I had 3 scoops, in that case I will see how will these 3 scoops, suppose in 3 scoops I have vanilla, mint choco chip and strawberry. All right, now I have to see that how will these 3 scoops, these 3 scoops are same, but what are the different ways in which they can be ordered. All right, now suppose I have 3 flavors. All right, if I have 3 scoops, what are the different ways in which they can be ordered? So the answer is actually 3 into 2 into 1, which is 6. There are 6 ways in which this vanilla, mint choco chip and strawberry can be, like, the thing is that these 3 flavors will remain same, but they're just ordered in 3 different ways. And if the 3 flavors are same and they're ordered in 3 different ways, I just want that to be 1 in this particular case. I don't want that to be 6 different cases. So I will divide by 6. All right, that's what there is to it. So the general rule is, if there are if your R, or basically the number of choices you're making, like here we have 2 scoops, right? If you had 3 scoops, then R would be 3, and you have to divide by R factorial, which is 3 factorial. 3 factorial or 4 factorial, whatever is the number of scoops that you're trying to do. And for that also we have a common notation, and the ordered, unordered, without replacement case actually just means that you are choosing. Like I have 10 flavors of ice creams and I'm choosing 2 flavors from it. That's all I'm saying. I'm not saying that what I'm choosing first, what I'm choosing second. I'm just saying, just tell me the 2 flavors you want. In that case, you calculate combination, okay? And that is notation, the notation is NCR and the formula is this. So basically this you remember, right? This was NPR, the ordered case, and we have already discussed, right, that you divide by r factorial. You divide it further by r factorial. Like here we divide by 2 factorial. 2 factorial is actually 2 only. 3 factorial is 6. So that's how you just divide it by that. So think of combinations as just picking r objects from n, not taking order into account. All right. Okay, are we good to go further? Let's go further. Now, this is the 4th case, which is unordered and with replacement. So basically, you can choose 2 scoops of the same flavor, and order also doesn't matter. Now again, here you can choose scoop 1 in 4 options, you can choose scoop 2 in 4 options. But again, this also takes order into account. How do you deal with that? Will it be like the same case as before? You divide it by 2 factorial? The answer is wrong, because this way of calculating works correct in without replacement case. If you have a without replacement case, then this works fine. But when you have with replacement, this will fail. And you have to think of another way to actually solve this issue, to solve the problem and count the total number of cases. So the best way is actually to consider bins. Okay, this is my flavor 1. I have bins of flavors. This is my flavor 2, this is my flavor 3, and this is flavor 4. So basically you consider this sticks, and I have flavors, I have scoops S1 and S2, and I can just put my scoops anywhere. So basically I have to arrange these 3 bins, not bins, these 3 sticks and my 2 scoops. So, and my 2 scoops. Alright, so these are the 5 cases, okay, and these are the 5 things I have to arrange. I can arrange them in 5 factorial ways. Alright, by principle of counting, like I can just do this, okay. But again, these 3 are not the same. Like these 3 are the same. We have defined it as 1, 2 and 3, but they're actually the same. So if I have scoop, stick, scoop, stick, suppose, all right, and 1, 2, 3, 1, 2, and if I have S2, S1, this is actually the same. It doesn't matter where stick 1 is, where scoop 1 is, right? So in that case, I have to actually divide it by the ordering of those. The ordering of the 3 sticks, which is 3 factorial, and the ordering of the 2 scoops, which is 2 factorial. And hence, I will get the answer as 5 factorial by 3 factorial, 2 factorial, and my answer is 10. And these are the 10 cases which you will see that are relevant for this case. The last case is actually the most difficult to understand, and you can let me know if you feel that this is something that you need more explanation for, and I can make another video for this as well. So these 4 cases are very important. You should know what they mean and how you should calculate or count the number of cases in each of the 4 scenarios that I have mentioned. I tried to make this as an ice cream parlor example so that you understand it better, make it will be more relevant to real life. I hope you enjoyed this video and you got a good understanding of permutations and combinations, and now solving problems would be much easier for you. Thank you all.